rewrite this formula, it will be Bs over K phi. We can't change the flux and we can't change the speed and torque by controlling B here, which means controlling the voltage of the stator. How can we control the voltage of the stator? Many methods. We can use AC voltage control. We discussed them, connecting two anti-parallel thyristors and two anti-parallel thyristors. We can control the voltage. We have on-off control. We have phase shift control. We already discussed them. Voltage feed DC link inverter. We discussed the inverter. We will discuss also pulse width modulation inverter. Example here, as you can see here, the torque speed. If B is 1, it means the voltage multiplied by Vs, it means the total voltage apply. This is the typical curve. But if it is reduced to 0.75, it means 75%, then the curve go down. And so you see, by controlling the voltage, by controlling B, the fraction of the armature stator voltage, we control the speed torque characteristics. We may control also the motor resistance speed by controlling the resistance on the rotor. Definitely, there we have a squirrel cage and we have one rotor type. Squirrel cage, it's blocked. We cannot access to the rotor, but in one rotor type, we can access because there is a brush and tooth, and we can then connect resistance, as you can see here. 3 resistances. We connect them to the 3 terminals of the rotor. And then we control these resistance, their value, we control the characteristics. See the characteristics here? It's moved to the right when we increase this resistance. But the problem here is this resistance, even we try to find it from the same manufacturer, there is even small bit difference between their values. And if their values are different, then this means that we have imbalance now system, which is not good, I mean, to deal with imbalance. So what we go for another option here. As you can see here, we connect the rotor to rectifier, and this is current as a choke, and one resistance here. But how we control it? By connecting a get turn off thyristor across it in parallel. When thyristor is on, then short circuit, the voltage is 0. When the thyristor is open circuit, let me say, the voltage here accounted. For how long it accounted depends how much when we pulse on and off the thyristor. In this way, we have one resistance for the 3 phases, and then this will give balance system. Sometimes what they do, they connect the rectifier, this is just filter for the current, and then inverter, and transfer back here, inject back the power from the rotor back to the supply. Okay, in this way they control the inverter, then they control the output, and then control the torque speed of the motor. And sometimes what they do, for each, let me say, terminal of the rotor winding, they connect thyristors anti-parallel in this way, as you can see here. So which one? Either they inject current here, or they take current from here to the supply for the 3 phases. This is slip power control system. Now, after we completed this application, just to remind you, we discussed the application for uninterruptible power supply and using a power electronic converter to, let me say, control the disturbances. And then we discussed the using of power electronic converter in air conditioning, in lighting, in welding, induction heating, and DC motor and AC motors. Now it's clear. The converters is clear for us. The applications are clear for us. Let's go for another point, which is the protection of these converters. From what we protect them? We protect them from electrical phenomena and thermal phenomena. Let me start with electrical. For electrical, as you know, when it's switch on and switch off, the rate of change of current and voltage is high. Okay, at the beginning, changing from 0 to the full load voltage with a small time in microsecond will give high value, which is we need to protect our switches, because these switches have limitations, and if we don't consider this, we may lose these switches. Also, the losses will increase if we don't protect them. Okay, and heat will come in, and then we may lose also because of heating. We have different circuits. The circuits are called snubber circuits. Snubber circuits, usually it could be unpolarized RC snubber circuit to protect diode and thyristor, or we may protect it by using RC to protect it from dV over dt, or LR to protect it from di over dt. Okay. Now let me explain this. Have a look at this circuit. I mentioned for this circuit early in this semester, where we have here a switch. This is the load. It's assumed to be a highly inductive load, so supply current, as you can see here. If the switch is open circuit, the current rotates through the diode here and so on. When we switch on, the current will follow here to the supply through the switch. Okay. Now we will put here, this is usually we assume, because we have wires, that there is stray inductance in the circuit. Okay. And we will put here resistance and capacitors connected in series in parallel with the switch we want to protect. Let me assume that I want to protect my switch, which is the diode here. Okay. Any switch, diode, thyristor, transistor, you can protect it by snapper. Okay. Now, for this circuit, if I come to the discussion when we discuss the operations of the diode, you remember what we mentioned? We mentioned that when you switch off, the current will flow through the thyristor, will reduce through the diode from maximum current into zero, then it go in the reverse direction and then back and becomes zero. And this is called time TRR, reverse recovery time, and the peak of this current is IRR, which is reverse recovery current. This is when we have a snapper circuit. Without a snapper circuit, the current will go higher than this, and when back, it will not back to zero. There is voltage to be blocked here. So how we protect this circuit, this diode? Have a look. When we connect the diode with the switch, okay. Now let's assume that at a moment we connect the thyristor, the switch. Okay, then what will happen? The current will follow, okay, in this way. By the way, the diode should be open circuit, and it should, the voltage here VD should apply across this diode. But what happened, because of the snapper circuit here, okay, the voltage will be built, not directly applied across the. Why it's built? Because the capacitor voltage will be built, because charging it starts as a short circuit and then it go for open circuit. So let me start discussing this circuit, snapper circuit, when we assume resistance is zero. At the beginning I will assume resistance zero and see the effect only of the capacitor. Then I repeat the discussion but considering the resistance R. So if the capacitor is only connected with the diode here, when we switch on the thyristor, the current will follow through the inductance and then through the capacitor, which represents short circuit now. Okay, because at the beginning it's short circuit, so you can see here, and there is no diode. Okay, the voltage across the capacitor is the voltage across the switch, the diode. Okay, now you can see here the voltage across the capacitor build. It's not directly jump to the maximum. No, it's built. It's increased until it's charged and then discharge in this way. Now, if I write formula for this equation, for this circuit, okay, the voltage will be the voltage across inductance and capacitor, and we will come up with second order differential equation. Let's assume at the beginning that the initial condition for the capacitor voltage is zero and for the current to be I reverse recovery time. Then when I try to drive a formula, I will find that VC equal to this expression here, where this expression contains C base. C base is these parameters together, and we have also omega naught. Omega naught is the critical, or let me say, critical angular frequency, which is 1 over square root L times C. And but see here the capacitor C. So if I control the capacitor, I control the voltage across the capacitor, then I control the voltage across the diode because it's connected in parallel with the diode. The maximum voltage found, if I drive the voltage here with respect to time and equate it to zero to find the maximum, I will find this formula. This formula represents the maximum voltage across the capacitor. Okay, I can't control it because this voltage is the voltage across the diode. If I control the voltage across the diode. So how can I control it? By controlling the capacitor. The ratio, taking VD here down, okay, over VD it means the ratio of the voltage with respect to the ratio of capacitor C base over CS is exponential, like exponential minus, or let me say square root of this ratio. So we control it By changing the ratio here, we change the maximum voltage and we can control it to reduce it as much as we can. Now, let's consider adding the resistance. If we add the resistance, why we add resistance here? By the way, in general, just simply speaking here, you know the capacitor with inductance is make like a resonance. I mean, charge, discharge, discharge. But the resistance here used to consume this power, this current. Consume inside the resistance when we add. When more control will come here. Okay. Now, if we repeat the same discussion through the finding equation, you see here R as came in the equation, and assume the initial condition, find the voltage, which contain now many parameters, omega A, alpha, omega naught, phi, all of them are parameters inside this equation. Okay, and then we go through the same procedure. If we go through the same procedure to find the maximum capacity voltage with respect to the capacitor, we can see that it's not only function of capacitor. Okay, it's function of the resistance also. Resistance came here to make an important contribution of the reduction of the voltage across the diode. Now the relationship between Vd max to Rs over Rb max, you see here. Now it's not only the capacitor which have effect, also the resistance have effect here, and it's changed the graph clearly. Okay. Now also the losses, now the power dissipated or energy dissipated in resistor in this circuit is part of it to be dissipated in the resistance, and part of it to be dissipated in the capacitor, and also there is part in the switch itself. Okay, so the total power dissipated is adding these losses together. Now, if I use one circuit, which is rectifier circuit, okay, fully bridge 6-pulse rectifier, then for each thyristor, as you can remember, we have thyristor 1, 3, 5, 4, 6, 2. For each one of them, I will connect what? Connect capacitor resistance in series as a snubber circuit. Now, this will help a lot. You remember when we discussed the commutation, when, as example, thyristor here, T3, will take over from T1. Now, when this happened, short circuit across 1 and 3 together, which is equal the voltage between these two voltage, VA minus VB, line to line, which is high voltage, apply across the resistor 1 to switch it off, it's high. So to reduce this effect, what we do, we connect capacitor in resistance here in this way. So when the current coming here to switch off, it will switch off here, not apply it here. It will apply across the capacitor, as you can see here resistance. So it will follow here and rotate. Capacitor voltage will be built, which is in parallel with the resistor. So the voltage across the thyristor also built. In this way, we reduce the effect. This is how it look like the circuit. T1, T3. Without this branch capacitor resistance, the current will follow here in this direction. But because of this capacitor, the current will follow across the capacitor and then switch to thyristor T1. Another problem could happen to our converter is the thermal, let me say, problems, and we need to protect it. This is coming from that our switches, the transistor or thyristor, have limited thermal capacity. Its resistive capacity is low. So what happen is, on the junction on the back of the thyristor or transistor, you find a metal, which is the junction here. It cannot handle heat. If heat increase, this will affect it may burn and we lose it. So what we do, we use case. Okay, by the way, insulator, we put insulator, then case, then insulator here, or let me say directly here and then insulator, and then we put heat sink. Heat sink similar to the radiator of the car. Okay, we may use only heat sink. We may use heat sink with air, with water, with fluid, with whatever, just to cool the case. Okay, the chip. Okay. Now, also this can be represented, as you can see here, the heat will taken from the junction to the case, from case to the sink, and from sink to the ambient. Okay, so you can see that the power across the junction, the temperature here, will move through thermal. R theta is thermal resistance. Okay, junction case, case sink, sink ambient is going to the ambient. These are different shape for this thermal, let me say, heat sink. Okay, they classify them into by numbers here according to the thermal resistance of sink ambient in Celsius per watt, and their volume is also written here. By the way, we prefer to have low volume because the size is an issue. Okay. Now the thermal junction resistance from the junction to the ambient is equal all the three resistances here, and junction ambient also equal to the temperature difference between junction and ambient divided by power losses. Let's apply this in this example. He told me the junction temperature of 125 Celsius transistor, 203 transistor, has a power dissipation. So he gave you the power dissipation 26. This is the power dissipation. And also he gave you the junction, okay, temperature is 125. The transistor manufacturer specify a value of 0.9 for junction case. Okay, he gave me junction case. Okay, this is junction case. Okay, here. And also he told me that a 75 micro thick mica insulator is used with thermal degrees, and the thermal resistance of the combination of is 0.4. So he gave me also the theta for sink ambient. Okay, the worst case ambient temperature in the cabinet where the heat sink is to be used is 55. So he gave me the temperature of the ambient, how much he wants. Now, if I substitute, okay, now in this formula, theta junction sink ambient. Sorry, he gave me junction ambient, sink ambient. I want it, which is this value minus all these values, and this value is represented by this formula. So this is T junction, and this is T ambient over P losses, and he gave me the theta junction ambient and junction case and case sink. So when I substitute, I got sink ambient. This is what I'm looking for. If I got sink ambient, okay, I go to this value, see which from the table, previous slide, which one is the closest one to this value. I got as example number 7, heatsink number 7, which have 1.3, which is close. It's preferable to be more than 1, but if we need to compromise here because size is an issue. So when we get the value, we can select from the table. These are different heatsink as example here for this fan. With this fan, you see here with air here, is used in our computers to heat cool the microprocessor because of heat. And I will stop here, and I hope that I gave my best to you in this semester, and looking to see you in another courses in another semester. Good luck and thank you.